So here comes an example where we're actually going to put it to use, this idea. Okay? Evaluate the area. We're going to go back to the old function that we used before, y equal x squared. So evaluate the area under the graph of y equal x squared on 0 to 1. But this time we're going to say by using n divisions or n intervals. And I leave n as is. I don't even assign a specific value. As far as we are concerned, n can be 3, n can be 10, n can be 100, n can be 1,000,000. All right? So, what do we do in this case? We know what is the value. Notice the other thing is, I didn't say approximate, I didn't say estimate, I say evaluate. In other words, we are expected to give the exact value. I already told you what is the exact value. I didn't show you why. I told you that the exact value is 1/3. You're going to see why it is correct now. So let's see how we deal with this. First, we want to graph again, even though we did it a number of times. So we go from 0 to 1, and of course, we go from 0 to 1 on the vertical axis. So here's a good old parabola, y equals x squared. And now what we're going to do is, I didn't give you specific number of sub-intervals. So we're going to start with the first interval right there, and if 0 equals x sub 0, then the first interval will be x sub 1, the next one will be x sub 2, the next one will be x sub 3, the last one will be x sub n, and the one before will be x sub n minus 1. So I did some generic divisions. And we're going to say the following. This is what we know. We know that x sub 0 equals 0. We know that x sub n equals 1. And we know that n is the number of divisions or number of intervals. Now, if the intervals are equally spaced, then delta x going to be always the difference between x sub n and x sub 0, the final value, minus the initial value divided by n. This is something that will be always true, provided that the intervals are equally spaced. This is something you need to be mindful. Very seldom we'll deal with intervals that are not equally spaced, but they exist, and at times we need to use unequally spaced interval, such that if you deal with logarithmic functions and so forth. But this is the condition. So if the intervals are equally spaced, then delta x is constant throughout, and this is the value of delta x. Now, let's do the following. We're going to say that r sub n will be the right endpoint sum of n intervals. Okay? And what is it equal to? It's equal to the following. It's equal to f of x sub 1 plus f of x sub 2 plus dot 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 plus f of x sub n times delta x. Okay. Using sigma notation, we're going to say it's equal to the sigma where an index I start at 1 and end up at n. And it will be f of x sub I times delta x. So I need to pause here and give you the first handout, or the only handout.